All right, let's talk about neural networks. I know. Just hearing the term can make you think of like crazy complex math and dense academic papers, right? Well, forget all that. Today, we're going to break it all down, but here's the twist. We're going to do it using concepts you as a developer already get. No jargon, just plain language. Ready? Let's jump in.
So here's the game plan. We'll kick things off with the big idea, rules versus learning. Then we'll talk about what a neural net really is. I call it the giant function. We'll look at the building blocks, neurons, and layers, and then the really cool part, how it learns, which is kind of like auto-refactoring code. We'll cover when you should and shouldn't use one, and wrap it all up with a solid mental model you can actually use.
Okay, first up, rules versus learning. This is really the fundamental shift in thinking, you know? It's the old way versus the new way, and it changes everything about how we approach problems.
So check this out. This slide basically says it all. In the world you and I live in as developers, we write the rules, right? We take some input, run it through our logic, our rules, and spit out an output. Simple. But neural networks, they completely flip that on its head. You give them the data, a ton of inputs and the correct outputs, and they figure out the rules for you. The machine writes the logic. It's a huge difference.
Let's make this real. Imagine you have to build a spam filter, the old school way. What do? You start writing a giant chain of if-else statements, right? If the subject has free money, mark it as spam. If the sender isn't in your contacts, maybe bump up the spam score. Oh, and if there are like a million exclamation marks, yeah, probably spam. But you can see the problem here. This thing is a nightmare to maintain. It's super brittle, and spammers are smart. They'll figure out a way around your hard-coded rules in like a day. It just doesn't work long-term.
So if we're not writing all those fiddly rules, then what exactly are we building? Well, let's reframe this whole thing. Let's think of it as just one giant function.
And that's really it. I'm serious. If you take away one thing, let it be this. At its absolute core, a neural network is just a function. A big, messy, complex one for sure, but still just a function. The magic isn't in the function itself, but in how it gets built. Instead of us writing the logic, the data automatically tunes all these internal knobs and dials until the function starts giving the right answers.
I love this analogy. Think about it like this. You've hired a junior developer, but you don't give them a spec. Instead, you just show them thousands of examples of here's what came in and here's what should go out. This junior dev just pores over all that data and starts to figure out the patterns on its own. The only difference is this dev works entirely with numbers, not lines of code.
Okay, so if the whole thing is just one giant function, what's it made of? What are the building blocks? Well, this is where we get into neurons and layers. First things first, forget everything you've heard about brains and biology. That stuff is just a metaphor. For us, a neuron is just a tiny, tiny little formula. It's a calculator. It takes some numbers in, multiplies each one by a weight, which is just how important that input is, adds them all up, and then runs that total through one last little function. That's it. And here it is in code, or at least something that looks like code. See? This should look totally familiar to any developer. It's just a function. You take some inputs and weights, do a dot product, add a little extra number called a bias, and then call another function on the result. Seriously, that's what a neuron is. It's just math we all know. No black magic involved.
So to break it down even further, the inputs are just numbers from whatever came before it. The weights, this is the important part, are the knobs that get tuned. They decide how much influence each input has. The bias is just a little nudge, an offset, to give it more flexibility. And that final activation function, that's the secret sauce that lets the whole network learn really complex, squiggly patterns, not just simple straight lines.
So what do you do with these simple little neurons? You just bundle a bunch of them together and boom, you've got a layer. Then you stack those layers on top of each other and you have a network. It's really that simple. Each layer gets its input from the one before it, does its own little transformation, and passes the result to the next. You know what it's like? It's exactly like a Unix pipe. You cat a file, pipe it to grep to find something, then pipe that to sort. Each step does one small, specific thing to the data. That's what layers do.
Okay, now for the million-dollar question. We've got this giant function made of layers of neurons. How does it actually learn anything? Well, my favorite way to think about it is like this. It's code that refactors itself.
The whole learning process is just a loop, over and over again. It goes like this. First, you push some data through the network from front to back. That's the forward pass. It spits out an answer. Second, you compare that answer to the correct answer. The difference between them, that's your error or loss. Third, and this is the clever bit, you go backwards through the network and figure out which of those little weights were most responsible for the error. Finally, you just nudge those weights a tiny bit in the right direction to make the error smaller. You do that a few million times, and believe it or not, you've got a trained network.
This whole process of nudging the weights has a fancy name, gradient descent. But you can just think of it like this. You're on a huge mountain, and it's completely foggy. You want to get to the bottom, the lowest point, but you can't see it. So what do? You just feel the ground right where you're standing, find the steepest downward slope, and take one small step in that direction. You just keep doing that, and eventually you'll find your way down. That's exactly what the network is doing with its error.
And sticking with this hiker analogy, there are different ways to get down the mountain. The most basic method, SGD, is just that simple fog walker, taking one small step at a time. But then you have smarter approaches, like the Atom Optimizer. Think of Atom as a smart hiker who has some momentum and remembers the path they've taken. They can adjust their step size, go faster on the easy parts, and be more careful on the tricky bits. Usually, these smarter hikers get to the bottom way faster and more reliably.
So to bring it back to something we all deal with, think of all those weights in the network as values in a giant .env file or some massive config file. And training the network, that's nothing more than an automated process that just keeps tweaking all those config values over and over until your application passes all its tests. It's just config tuning, but on a mind-boggling scale.
Okay, that was a lot. You might be thinking, wow, that sounds like a ton of work and complexity, and you're not wrong. So why would anyone even bother with all this? And maybe more importantly, when is it a terrible idea? Let's do a little reality check.
So here's the payoff. The whole reason we go through this trouble is because neural networks are incredible at figuring out messy, complicated relationships in data. They can approximate functions that you or I could literally never write the rules for by hand. I mean, how would you write an if statement to recognize a cat? You can't. And that's why they're king in areas like image recognition, speech-to-text, self-driving cars, and yeah, the huge LLMs everyone's talking about. They eat real-world complexity for breakfast.
But we also need to bust a few myths here. First, neural nets are not magic. They're just a ton of math and a ton of data. That's it. Second, throwing more layers at a problem is not always the answer. Sometimes it makes things worse. Third, and this one's important, they don't understand anything. They are just ridiculously good at finding patterns. And finally, and this might be the most important takeaway for a practical developer, sometimes a simple little bit of regex or a basic algorithm is absolutely the right tool for the job. Don't use a sledgehammer when you need a screwdriver.
All right, let's wrap this all up. Let's build that final, developer-friendly mental model that you can walk away with.
So from now on, when you think about neural networks, think about them like this. 1. It's a function that literally writes itself using data. 2. Training is basically just unit testing at a massive scale, where every failure helps it refactor itself. 3. All those weights and biases, that's just mutable state that gets tuned over time. And finally, things like PyTorch and TensorFlow, they're just your standard libraries. They're the frameworks that hide all the nasty math so you can focus on building the cool stuff.
And so that really leaves us with just one question to ponder. Now that you can see a neural network for what it is, not some scary alien tech, but a powerful tool for getting the data to write functions that we could never code by hand, what impossible function are you going to build?